Welcome, this is Mr. Anderson, and this is Probability and Quantitative Reasoning. And this is our Chapter 4.1 through 4.3 review. This is Section 4.1. Hope to make this about a 15-minute review, and I'll have to move through this rather quickly in order to make that goal. Let's move on to question number 1. All right, in the top left, I've got the problem number. In the top right, I got the section number. This is so you can scroll through the video rather quickly to get to the problem that you specifically want. The problem numbers correspond to our homework review. It says if A denotes some event, what does A not denote? If the probability of A equals 0.009, what is the value of the probability of A not? Okay, so what does A not denote? Well, let's just assign A to something. Let's say that the event A is me putting everybody's name into a hat, the class's names into a hat, and I draw a name out, and event A is me drawing your name out of the hat. Then A not would be me not drawing your name out of the hat. One of the two things has to happen, either A or A not. One of those two things has to happen, me drawing your name or not drawing your name out of the hat. Event A not denotes the complement of event A, meaning that A not consists of all outcomes in which event A does not occur. That would be B here. Down here it says the probability of A equals 0.009. So let's say the probability of me drawing your name out of the hat is 0.009. What is the value of the probability of A not? Well, they both have to add up to 1 because one or the other has to happen. It's certain to happen. If something's certain to happen, it is 1. One or the other is happening. So 1 minus this 0.009 is 0.991. All right, next question. Problem 2, we all know a probability is a number between 0 and 1 inclusively, and we are selecting all the values that cannot be probabilities. A is a negative number. That is not a probability, so we'll check that one. B, that's a probability. 0, we include 0. C, 5/3, that's greater than 1, so that is not a probability. D, 0.05, that's between 0 and 1. E, 1, we include 1, that's certain to happen. 3/5, that's between 0 and 1. 1.52, that's greater than 1. And square root of 2, that's 1.414. So that is greater than 1. That is not a probability. Problem 3. Assume that 2,400 births are randomly selected and 72 of the births are girls. Wow, that sounds really low. Use subjective judgment to describe the number of girls as significantly high, significantly low, or neither significantly low nor significantly high. All right, so we're just using subjective judgment. Things that we know, experience from our past. 2,400 births, we expect there to be about half of them girls, half of them boys. And 72 is really, really low. We expect to be there about 1,200 of them to be girls. So we'd say this is significantly low. Problem 4. For a certain instant lottery game, the odds in favor of a win are given as 3 to 97. Odds in favor is successes versus not successes. We break it apart. The total we break apart to successes and not successes. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusively. Well, we know the probability is successes over total. We know what the successes are. That's 3. And then the total, like if I was to put everything into the hat, that would be the successes and the not successes. So I just add the 3 and the 97 together. That's the total. Oh, I just put successes again. So 3 is our successes, and the total would be 3 plus 97, which is 100. And that is 0.03. Next question. Whoops, I skipped one. Problem 5. In a certain study, the chance of encountering a car crash on the road is stated as 24%. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusively. Very handy to think of probabilities expressed as percentages because they build a lot of intuition into the problem. Right? But we need to know how to write them also as probabilities. So 24%, you'd write percent the same way you'd write cents, like dollars and cents. You'd write 24 cents like 24 cents like that. But we're not going to write the dollar sign. We just want to write 0.24. That is the decimal equivalent of 24%. Problem 6. Express the indicated degree of likelihood as a probability value between 0 and 1. Based on a survey of hiring managers who were asked to identify the biggest mistakes that job candidates make during an interview, there is a 50-50 chance that they will identify inappropriate attire. 50-50 chance. What are they saying here? 50-50. 50 success, 50 not success on inappropriate attire. Success, not success. That sounds like odds to me. Success versus not success. 50, 50, 50. Success, not success. Well, I know probability is success over total. Well, I know what the success is 50. Total is the successes and the not successes added together. That's 100. And you might intuitively know that this is 0.5, or expressed as a percentage, 50%. This is a common slang thing to say, 50-50. But in fact, this is where it would come from. 0.5. Next question. Problem 7. You are certain to get a queen when selecting 49 cards from a shuffled deck. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusive. You are certain to. When students get this wrong, they usually miss this right here, and they're reading all of this right here, and they're paying attention. 49 cards. How many cards are there in a shuffled deck? Oh my goodness, what do I look at? What do I look at? This is all I really need to know. You are certain to. It doesn't even matter what the event is. If it is certain to happen, it is a probability of 1. Next question. Refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? Who would suffer from a false positive result and why? False positive. Okay, well, let's take a look at all the positive test results right here. These are positives, and these are positives right here. A false positive is when the test is positive, but it's wrong. But it's wrong. Okay, so that means that it's tested positive for drugs, but they were not a drug user. So this right here tested positive for drugs, but they were not a drug user. This is what we're concerned with right here. Here, they tested positive for drugs, but they were a drug user. So this would be a true positive. Over here, these are the negative test results over here. The 12 represents negative test results, and they used drugs. It says the test said they didn't use drugs, but it was wrong. They actually did use drugs, so that's false negative. Whoops. False negative. And the bottom one must be a true negative. The test said they didn't use drugs, and they in fact did not use drugs, so that's a true negative. Okay, so back to the question. The probability of a false positive. False positive is successes over total. Alright, so that's this 15. That's the success of that event happening, a false positive happening, over the total of everything added up. The 43 plus 15 plus 12 plus 31, I get 101. So we got 15 divided by 101, and I get 0.149 as a probability, 3 decimal places. All right, who would suffer? Just use your best judgment here. I'd say that the person tested would suffer because he or she would be suspected of using drugs when in reality he or she does not use drugs. You could make an argument that certainly the employer does not want to be accusing people wrongly of using drugs when in fact they didn't use drugs, but I think this is the best answer. Next question, number 9. In a survey of consumers aged 12 and older, respondents were asked how many cell phones were in use by the household. No two respondents were from the same household. Among the respondents, 205 answered none. 282 answered 1. 361 said 2. 145 said 3. And 78 responded 4. 4 or more. 4 or more. Okay. A survey respondent is selected at random. Find the probability that his or her household has 4 or more cell phones in use. Is it unlikely for a household to have 4 or more cell phones in use? Consider an event to be unlikely if its probability is less than or equal to 0.05. They specifically tell us what unlikely is. Probability of 4 or more is going to be successes over total. So we have 78 successes that responded with 4 or more, and the total of all these added up was 1071. That gives me a probability of 0.073. This is not greater than 0.05, so this is not unlikely. It's close, but it is not greater than 0.05. So this is not unlikely. I would say B. Is it unlikely? No, because the probability of a respondent with 4 or more cell phones in use is greater than 0.05. Problem number 10. To the right are the outcomes that are possible when a couple has 3 children. Assume that boys and girls are equally likely, so that the 8 simple events are equally likely. Find the probability that when a couple has 3 children, there is exactly 1 girl. All right, so they said 8 simple events. That's these 8 simple events right over here. 1, 2, 3, 4, 5, 6, 7, 8. Notice that these 8 simple events are all the events that are possible to happen. All of these events added up make up the sample space. The sample space. That's what that's called. All right, because one of these 8 things must happen. One of these 8 events must happen. Okay, and what is the probability of exactly 1 girl out of 3 children? This is going to be successes over total. Let's see how many successes we have. Let's look at these 8 simple events. How many of these do we have exactly 1 girl? Not this one. Here is exactly 1 girl. Here is exactly 1 girl. And there's 2 girls. This is exactly 1 girl. There's 2 girls. There's 2 girls, and there's 3 girls. So 3 of the 8. 3 of the total of 8 have exactly 1 girl, and that's our probability. All right, next question. The same space, the sample space listing the 8 simple events that are possible when a couple has 3 children that we just saw in the previous problem. After identifying the sample space for a couple having 4 children, find this probability of getting 1 girl and 3 boys in any order. All right, so this part's a little bit tedious and it'll take me a little bit. But I think one way that we could help keep our thoughts organized about this is using a tree diagram. So on our first birth, we could have either a boy or a girl. Now, on our second birth, we had a boy on our first birth, we could have a boy or a girl. Or if we had a girl first, we could have a boy or a girl. Now on to our third birth. If we had a boy and a boy first, we could have a boy and then a girl. A boy or a girl. Or if we had a boy then a girl, we could have a boy or a girl. If we had a girl and then a boy, whoops, kind of messed that up. We could have a boy or a girl. And same thing here, boy or a girl. So these are all the possibilities. 1, 2, 3, 4, 5, 6, 7, 8. These 8 twigs on our tree here represent these 8 simple events. All of these together make up the sample space of having 3 children. Now we continue it on to make the sample space for 4 children. All right, they have the first 3 boys. The 4th kid could either be a boy or a girl. And on down the line, we could have a boy or a girl. We could have a boy or we could have a girl. We could have a boy or we could have a girl. We could have a boy, getting a little sloppy here, or we could have a girl. We could have a boy or we could have a girl. We could have a boy or we could have a girl. We could have a boy or we could have a girl. And you see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different possibilities in our sample space. But one of these 16 things has to happen. 16 simple events in our sample space. All right, so I've got to list all these things out now. Let's see if I can do this without error and quickly. All right, let's type these in real quick. Okay, now real quick here. I'll just show you what I'm doing here. Okay, so here's what I'm doing. Here is one route. I could have all boys, or I could take another route. I could have first one's a boy, second one's a boy, third one's a boy, and last one's a girl. Take another route. First one's a boy, second one's a boy, third one's a girl, and last one's a boy. Or take another route. First one's a boy, second one's a boy, third one's a girl, and fourth one's a girl, and so forth. You just follow the tree till you get to the very end twig. All right, and that's what I'm going to do as I enter all these in here. Oh, there we go. Let's make that smaller. Okay. Get these in. Okay. I could have boy, 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 girl, boy, boy, girl, boy, 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 girl, girl, boy, girl, boy, 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 wait, boy, girl, boy, girl, alright, boy, 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 girl, boy, boy, girl, boy, 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 girl, girl, boy, girl, boy, 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 girl, boy, girl. Okay, there we go. Boy, girl, got it. Boy, girl, girl, boy, boy, girl, girl, girl. And then we go on to the girls. Girl, whoops, girl, boy, boy, boy. Well, let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, and I'm on my 9th one. Good. Girl, boy, boy, boy. And then I got girl, boy, boy, girl, Oh, I'm supposed to put a comma between it. Girl. Boy, boy, girl. Girl. Boy, girl, boy. Girl, boy. Girl, girl. Girl, girl. Boy, boy. Girl, girl. Boy, girl. Girl, girl, girl. Boy. Girl, girl, girl. Girl. Alright, that should be it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I got it right there. Okay, so the second question is find the probability of getting 1 girl and 3 boys in any order. Oh, we're already at 20 minutes on this video, 21 minutes. I guess it's going to be a little bit longer. That's all right. Okay. Find the probability of getting 1 girl and 3 boys in any order. All right, so I'm going to go back to my sample space here and look at all these simple events. I'm going to find every one of these that have 1 girl and 3 boys and just check off. So this one has 1 girl, 3 boys. This one, 1 girl, 3 boys. 1 girl, 3 boys. Whoops, not that one. 1 girl, 3 boys. And that's it. So 4 of the 16 have 1 girl, 3 boys, or 1/4 of them. They want a decimal, so 0.25. All right, next question. Problem number 12. Okay, use the given probability value to determine whether the sample results could easily occur by chance, then form a conclusion. A study on the enhancing effects of coffee on long-term memory found that 35 participants given 200 milligrams of caffeine performed better on a memory test 24 hours later compared to the placebo group that received no caffeine. Okay, so A, there was a probability of 0.049 that the difference between the coffee group and the placebo group was due to chance. What do you conclude? This is a good time to think of this probability, express this probability as a percentage, just to give us some intuition into the problem. So think of it this way, a 0.049 probability. How about we say it expresses as a percentage? That would be, here we go. That would be 4.9%. That's a 4.9% likelihood that this is just due to chance. That's not very likely that it's just due to chance. There's something here. There may be something here. So my conclusion is that the probability shows that the sample results could or could not have easily occurred by chance. I would say could not. Could not have easily occurred by chance. And it appears that there is sufficient evidence to conclude that 200 milligrams of caffeine does have an effect on memory. There may be something here. B, a group given a higher dose of 300 milligrams performed better than the 200 milligram group, with a probability of 0.75 that this difference is due to chance. What do you conclude? All right, let's do the same thing here. Let's convert that probability of 0.75 to a percentage, just to build some intuition into the problem. 0.75, that'd be a 75%. 75% chance. What? 75% chance? 75% likelihood that this is just due to chance? This is a good chance this is just due to chance. The probability shows that this sample results could or could not have easily occurred by chance. It could very well have just occurred by chance, because there's a 75% likelihood this just occurred by chance. It appears that there is not sufficient evidence to conclude that the effects from the 300 milligram treatment and the 200 milligram treatment are different. Next question. 13. A modified roulette wheel has 40 slots. One slot is 0 and the other double 0, and the others are numbered 1 through 38 respectively. You are placing a bet that the outcome is an odd number. In roulette, 0 and double 0 are neither odd nor even. All right, so these 1 through 38 are the odds and evens. So half of those are odds, half of those are evens. So we got 19 odds, and we got 19 evens, and then we got 2 that are neither. All right, so that makes up our 40 different slots, right? So the probability of winning, the probability of an odd then would be successes over total, and our successes are our odds right here, the odd numbers. We've got 19 of those. So we got 40 total slots in the hat. One of these 19 is a success out of a total of 14. All right. They want a simplified fraction, so we're just going to write it that way. 19 out of 40. What are the actual odds against winning? Now when we write odds against, remember odds in favor, we write successes versus not successes. Odds against, we write it not successes versus successes is how we write that. We split apart the total, we split apart the successes and the not successes. Well, we know, okay, so imagine you got these 40 slots in your hat, right? If you take out the 19 successes, what are you left with? You're left with the not successes in the hat, the 21 not successes left in your hat. The 19 evens and the 2 neithers, those are your not successes. So we'd have 21 to 19 odds against. So remember, odds in favor would be just reversed. Successes versus not successes. When you bet that the outcome is an odd number, the payoff odds are 1 to 1. Payoff odds, they are, that is, how would I call that? Net winnings. Net winnings versus your bet. All right, and you can write that as a fraction. You'd write it net winnings over B. Just like this, you could write as a fraction not successes over successes. You could write your odds against. Okay, so how much profit do you make if you bet $11 and win? Well, this one's kind of obvious because it's 1 to 1 odds. It's obviously you win $11, but this is how you'd calculate it. All right. So for other calculations, it's kind of important how we make this calculation. We take the $11 and then we multiply it by the payoff odds in a fraction. Here we have the net winnings is $1 and the bet is, well, yeah, it's 1 to 1. The payoff odds are 1 and 1 to 1. So 11 times 1 over 1, which is just 1, we win $11. Okay. Now, how much profit do you make on $11 if you could somehow convince the casino to change its payoff odds so that they are the same as the actual odds against winning? What you're basically saying is, hey, casino, don't make a profit, just do this for my benefit of fun. And so we want the 21 to 19 odds instead as our payoff odds. So we multiply the $11 times 21 over 19, and I get $12.16. Okay, next question. The blank for procedure consists of all the possible simple events for all outcomes that cannot be broken down any further. remember the simple events of having 3 children. All right, there's 8 different simple events. All those grouped together. Boy, girl, and boy, girl, boy, girl, boy, girl, boy, girl, boy, girl, boy, girl. 1, 2, 3, 4, 5, 6, 7, 8. All those simple events all together made up the sample space. One of these 8 simple events has to happen. All possible simple events. Each one of these little twigs is a simple event. Okay. Next question. Fill in the blank. The classical approach to probability requires that the outcomes are, there's 3 different types of approaches to probability that we talk about in class. One is relative frequency. We just take a look. How often did it happen in the past? How likely is it that a male senior in high school gets into an accident with a specific type of car and causes $5,000 worth of damage? I just take a look. How often has it happened in the past? That's how often I expect it to happen in the future. That's relative frequency. Relative frequency approach to probability. Another approach to probability is a subjective approach to probability. I just use the information that I have already up in my brains, the experiences that I've had in life, and I just kind of eyeball things and estimate. Hey, I think that probably will happen. The classical approach to probability requires that the outcomes are equally likely. When I throw a die, it is equally likely that I roll a 1, a 2, a 3, a 4, a 5, or a 6. When I flip a coin, it is equally likely that there's a heads or a tails. When I have those 3 children, any one of those 8 simple events is all equally likely. As a procedure is repeated again and again, the relative frequency of an event tends to approach the actual probability. This is known as. All right, so I flip a coin one time and I get a heads. I get heads. Okay, I'm not surprised at all. It's got to be either heads or tails. I flip it again and I get another heads. Wow! No, I'm not surprised. That's not that unusual, really. And then I flip it again and then I get a tails. I'm like, okay. So what? No big deal, right? And then I flip it again and I get a heads, right? You're like, what's your point, Mr. Anderson? This is nothing unusual. Get to the point. Well, the thing is, okay, so look, there's 3 out of the 4 times this was heads. Wouldn't you expect it to be 50%? Isn't that kind of unusual? You're like, well, no, you only tossed it 4 times. That's not very unusual at all. I was like, but it's supposed to be 50%. You're like, no, throw it a bunch of times. And you're right. You're right. The more I throw it, maybe I get tails, tails, tails. I get a run of tails here. And I get heads and tails and tails and heads. Whoops. Oh well. There's a heads and a heads and a tails and a heads and a tails and a heads and a tails and a heads and a heads and a heads and a tails and a heads and a tails and a tails and a heads and a heads and a tails and a heads. All right. The point is, I'm not surprised with these first 4 that 75% of them were heads. I'm not surprised at that at all. I only threw 4. All right, but if I threw 10,000 of them, I would be very surprised if 75% of them were heads. I say, hey, that is a fishy coin there. That is not a fair coin. There's something wrong with that coin. Right? Because the more and more I repeat that procedure, I expect it to get closer and closer to the actual probability. As a procedure is repeated again and again, the relative frequency of an event tends to approach the actual probability. This is known as the law of large numbers. If I threw that coin 10,000 times, I wouldn't expect it to be exactly 5,000 times head, 5,000 times tails. But I would expect the percentages to be, somewhere near 50-50. Somewhere around 50%, All right, I think that's the last question for this section. Yes. I hope this review was helpful. Our next video is on section 4.2, and I will see you in class.